Hello everyone, we are Group 32, and today we'll be presenting our project on CDC diabetes health indicators. Next slide, please. Our team includes Glenn, Jesslyn, Lester, Youth, Bryce, and myself, Micah. Next slide, please. So, why does diabetes prediction matter? Well, diabetes is a major global health issue affecting millions of people, even my dad. So, if left undiagnosed or untreated, it can lead to severe complications. However, early detection can make a significant difference in preventing these risks. This is where machine learning comes in. It helps improve prediction accuracy, making early diagnosis faster and more efficient. So, what is our project about? It is about developing a machine learning model to predict diabetes based on behavioral risk factors, which identifies key factors that contribute to diabetes while exploring the relationship between lifestyle choices and diabetes risk. So, why is it important? Early diagnosis helps in preventive healthcare and timely intervention, which means data-driven insights, which uses real-world health data for better understanding, and it is more efficient as it can assist in screenings and decision-making for healthcare professionals. So by leveraging machine learning, we aim to provide meaningful insights that could contribute to diabetes prevention and management, ultimately improving public health. I will now pass the time to you to talk about our literature review.
Thank you, Micah. Now let's take a look at our literature review. We focus on Sinyi studies, diabetes prediction, which aim to identify the key features that strongly correlate with diabetes and to develop a highly accurate predictive model. To achieve this, Ren began by employing a correlation heat map to explore the relationship among the features, which was then complemented by a chi-square test to statistically validate their relationship. This dual approach allowed her to narrow down the original 21 features to the 15 most relevant predictors, ensure that both continuous and categorical variables were appropriately considered. The dataset was subsequently divided into 80% training and 20% testing set to rigorously validate the model performed on unseen data. In the processing phase, smooth was applied to address class imbalance and a common issue in medical datasets, and feature scaling was used for normalization to ensure that each feature contributes equally. Finally, permutation feature important PFI was used to quantify the impact of enhancing the overall interpretability of the framework. This comprehensive methodology results in the predictive model that is not only highly accurate insight for the future research in diabetes prediction. Next, we're gonna talk about the advantage and disadvantage of the study, and Bryce will brief this.
Thank you, Yute. Now, for some of the advantages, included its feature selection approach, which combined correlation analysis with chi-square test to efficiently identify the most relevant predictors of diabetes. Then, they used SMOTE for oversampling, which helped address class imbalance across multiple models, while PFI was used to provide clear insights into feature contributions. However, there were some limitations. Although the CAT-BOOST classifier achieved reasonable overall accuracy, its precision was lower than expected, leading to misclassifications between diabetic and non-diabetic cases, and vice versa. Since SMOTE was applied only to the training set, the test set remained unbalanced, which contributed to overfitting in models such as decision trees and random forests. Additionally, relying solely on the 2015 dataset limited how well these results applied to more current data or different population sizes. Next slide, please. So this slide summarizes the accuracies and precisions of the models tested in the previous study. So their results will serve as our benchmark, and one of our primary goals was to improve the test precision score. And now I will pass my time on to Glenn, who will discuss on our own approach to address some of the limitations in the previous study.
Thank you, Bryce. So on to our approach overview. As mentioned earlier, we use the diabetes health indicators dataset from Kaggle to develop supervised learning models for predicting diabetes. We began with data cleaning to handle unclean data such as missing values and outliers, followed by exploratory data analysis to identify risk factors. Then we perform feature engineering to create new features and use techniques like chi-square and correlation matrices for feature selection. Finally, we also compared multiple machine learning models to determine which one performed the best. So on to early stage research and hypothesis building. We were able to back our hypothesis with some examples being taking high blood pressure and high cholesterol to form hypertension risk, as well as physical activity, alcohol consumption, and smoking to form lifestyle risk, both of which are also factors that contributes to diabetes outcomes. We also visualize bar charts, box plots, and examine the correlation metrics to understand how different features affect or relate to the target variable. So lastly, in early stage experimental settings, we tested our hypothesis by applying feature transformations and refining feature selection. After testing out the model prediction with imbalanced dataset, we also balanced our data using oversampling and undersampling methods to improve model accuracy. These steps laid the groundwork for robust, data-driven insights into diabetes risk prediction. Thank you, and I will now pass the time over to Lester.
For our second approach, we categorize BMI using the CDC's obesity scale to define a high-risk factor feature based on their diabetes risk factors, including high cholesterol and high blood pressure, as well as a poor lifestyle factor from our previous experiment. Afterwards, we performed a chi-squared test for feature selection and tested different sampling strategies for our imbalanced dataset. Next. Our best sampling strategy was undersampling using Tomat links. We can see that tree-based classifiers and MLP perform very well on the imbalanced datasets. However, after undersampling, we can see an increase in recall and a slight decrease in precision, meaning that our model is better at identifying diabetic patients, but it's also classifying more non-diabetic patients as diabetics. Given the trade-off in precision is very low for higher recall, our evaluation is that our best model is still XGBoost with undersampling. Next. For other sampling strategies, we observe significantly higher recall for diabetic patients in oversampling, but lower accuracy overall. Undersampling had poor performance across all metrics due to information loss on our majority class. And finally, both sampling strategies had significantly impacted our training and model fitting time. Next, I will pass off to Jess for the conclusion.
Thank you, Lester. To summarize, we developed a diabetes prediction model using multiple machine learning algorithms and applied feature selection and data resampling to address class imbalance. Among the models tested, XGBoost achieved the highest accuracy, 89%, while CatBoost demonstrated strong precision, 55.6%. Next slide. Through SMOD and TOMIC links, we enhance prediction performance, and our feature importance analysis confirmed that BMI, age, and blood pressure are key indicators in diabetes risk assessment. Moving forward, we plan to refine our approach by testing CatBoost on our dataset, optimizing hyperparameters, and investigating practical healthcare applications. Our results emphasize the potential of machine learning in early diabetes detection and prevention, contributing to improved healthcare outcomes. Maybe as for future improvements, we could explore deep learning techniques, enhance assembly methods, and incorporate additional medical history data to further refine model performance. Thank you for your attention, and we look forward to your questions.